we will continue today our journey. And this is our roadmap. As I mentioned yesterday, we want to see what are the opportunities and challenges of edge artificial intelligence from the hardware-software co-design perspective. Yesterday, we covered quite a lot about what we can compute at the edge and how we can do that effectively. And today, we will start exploring how to compute. In more direct terms, we will transition from software to hardware. So this is what we covered yesterday. We looked about different ways to do smart acquisitions in an efficient way with compressed sensing or event-based and similarity. And then we look at how to interpret those acquisitions, either by extracting features and then doing some type of classification, or by using deep neural networks. And each of these two flows present different characteristics which kind of complement each other. These were the two flows, feature-based, in which we condition the signal, we do some data fusion, feature extraction, and then classification, and a machine learning or artificial intelligence type of flow in which we have signal conditioning and then we just throw the conditioned data into a network. Not unsurprisingly, these two types of flow have different computational characteristics which we can leverage in order to make a domain-specific architecture. If we look at the feature-based, we have a decent level of task-level parallelism, not the type which you can expect in GPU style of applications, but still, maybe we can do something with multiple cores. And then these are characterized by a set of intensive computational kernels. The rule of thumb is that feature extraction application spends 90% of its time into 10% of its code. So there are computational hotspots which we can hope to accelerate and execute in an efficient way. There is a moderately complex control flow. So as opposed to what you may find in machine learning, for feature extraction, there are definitely if then else. So if we want to accelerate this type of structures, you better deal with it. And there is some resiliency, at least to a moderate degree, towards errors. For in the machine learning case, we have a huge amount of data level parallelism, linear algebra, which very largely dominates runtime, so we better accelerate for that. We have very regular or control flow or none at all, so we may have a structure in hardware which is very light from a control perspective in order to maximize data intensity. And we are very much resilient towards errors. These are characteristics which can be harnessed in order to build a domain-specific architecture. In the next hour or so, I will give multiple examples on how this can be achieved. So we are back to the hardware-software co-design pattern in which we have edge applications and edge systems, and these have contrasting demands. Edge application would like to become more and more complicated. Edge systems would like to be more and more efficient. So domain-specific specialization is what allows us to marry those two requirements. And this is a very challenging topic, and is so much challenging that after the end of the Moore's law, computer architects are willing to sacrifice what were fundamental concepts in how computing machinery works. For example, von Neumann machines postulate a separation between computation and storage, and this has been a fundamental tenet since the early 50s when building machines. But now we're challenging that, and how many of you follow news Coarse in the morning? Okay, so you know quite a lot about computing in memory and why we want to do that. analog computing is also something which has been around the last time in the 40s, and from the 1940s onward, it was well established that computing should be done in the digital domain. But nowadays, confronted with the end of technology scaling, we are willing to sacrifice even that in order to have increasing performance and efficiency. So this opens a very wide landscape of possible solutions, which has been termed in this paper the Cambrian explosion of computing architectures. Does anybody know what the Cambrian period was? So in geological terms, this is the period where life differentiated from unicellular molecules to a wide differentiated version of life forms. And we are assisting to something similar in computing architectures in order to cope with the increasing requirement of machine learning application and the end of Moore's law. Enough of philosophy. Let's start with some practical solutions, and it looks at feature-based flow first, and at solutions which may leverage task-level parallelism and moderately complex control flows. A good place to start, I think, are processing cores. And there was a period in the first and second decades of the 2000s in which there was a flurry of different processing cores being proposed in academia for edge applications based on customized instruction set like the FIRAT or on RISC-V instruction set like the PULP and the PULPissimo core. In order to build these cores, the main choices were the selection and the type of instructions in the instruction set, the admitted operating voltages, and the supported voltage modes. The best solutions toward the edge tended towards minimalistic architectures in which the instruction set was very much reduced in order to have simplicity and less efficiency, and which can lead to implementation which have a high range of possible voltages and frequencies. Of course, if you have a higher voltage, you can support a faster frequency, while if you have a lower voltage, you can support operations with a lower energy envelopes. More on that in a few slides. Then, basically, all of them supported different types of low power management and different deep sleep modes. Let's look at one of these processors which were developed into my lab by a PhD student which graduated a few years ago, and the name is Ahmed Dogan. And what he proposed was called FIRAT, which is a very small 3-stage pipeline with 16-bit data paths, 24-bit instruction size. And what he aimed to achieve was to have the lowest clock per instruction possible. When you have this type of architecture, you are allowed to spend some of the real estate in order to specialize it a little bit. In this case, the specialization was very lightweight. We just wanted to support multiple bit shift in one cycle for the type of application which we wanted to run on this architecture. So, what he achieved was a design which scaled pretty well in the range of ultra-low power applications from 10 megahertz to 1 megahertz, working at voltages which were pretty low, from 0.7 to 0.5 volts. Again, this is why we want to work at low voltages, because the dynamic power consumption decreases dramatically as we lower the voltage supply up until a certain threshold where leakage starts to dominate. But this crossing point is usually pretty low, and at these levels you start to have a bunch of other problems related mainly with the reliability of SRAMs. Again, more on that later on in this lecture. So, short pipeline, so we could have very few stalls in the execution, and this led to very few clock cycles and an efficient implementation for the type of biosignal monitoring application which we were looking at, which was filtering. In this case was morphological filtering, if you remember of yesterday, and compressed sensing. It turned out that, yes, that architecture was simple, but it's not simple enough. If we simplify things further, we can achieve even more efficiency. And this was the second design from Ahmed, and this was still a 3-stages pipeline. And in this case, we could reuse the output register from the ALU, doing some data bypass and bypassing the register file. Very minimalistic instruction set, only 11 instructions, and we added a special instruction to support compressed sensing, and this special instruction was doing the multiply accumulate with a random matrix composed by zeros and one. You can imagine that you can implement such a randomizer very efficiently with the linear feedback shift register. Does anybody know what a linear feedback shift register is about? It's basically a shift register with some feedback connection with source, which generates a strings of zeros and ones, and can use that in a custom instruction in order to implement efficiently a matrix which only contains zeros and ones. This was our custom instruction. So things were going pretty well. You can see that if we look at the number of clock cycles required for our applications, Tamarisk was even more efficient than FIRAT, due on one side to the fact that we could bypass the register file and use the output register of the ALU as an operand, and on the other side, for the compression application, we could use our custom instruction. This design was actually taped out. Here you can see the tape out of the chip. If I remember it well, it was 90 nanometer technology. Take that with a grain of salt. And we actually embedded that into a biosignal acquisition device. And we could see that using the compressed sensing algorithm, we could increase the lifetime of the device with respect to streaming the data with Bluetooth low energy. Because wireless costs energy, so the least data we can just stream on the wireless channel, the more efficient we are, so the lifetime of the device for a given battery increases. Questions about that? Yes?
We are supposing that they are running at the same frequency?
So, in FIRAT and Tamarisk, they were running at the same frequency. In this example, the MSP430 was not. I honestly don't remember the exact frequencies. I'm sorry, you have to look it up in the paper. Other questions? Okay. Now, we have a core. This is kind of a nice building block to start having systems. And the first thing that you want to do once you have a single core is, okay, now I want to have multiple cores. And this was our first trial of having an edge, ultra-low power, multi-core system for biosignal analysis. It has multiple Tamarisk processors, and each have their own private instruction memory, so the instruction memory plus the core makes a single processing unit. And then we have a common data memory. The idea here being that in this way we can have applications which are mapped into different regions of this multi-bank memory, and that if some data can be accessed at the same time by multiple processors, then we can have some efficiency gains there. We used a crossbar, which allows us to stall cores in case of conflict, so if multiple cores access the same bank in the same clock cycle. With multiple processors, we could deal with applications which process multiple streams of data at the same time. And this is a common case if you think about biosignal acquisitions, but even in other scenarios like environmental monitoring and so on and so forth. So these are details of how the architecture was implemented. So the data memory was shared, 16 banks, 64 kilobytes, private instruction memory, and each processor executed its own program. Now, what we wanted to investigate with this type of architecture is a question by Seymour Cray from Cray Supercomputers, which was kind of making the case against GPUs. And he was asking, would you rather use 2 oxens or 1,024 chickens to plow a field? In this case, history tells that he was rather wrong, because we nowadays prefer to use many, many chickens instead of few oxen. Nevertheless, even for deep, ultra-low power edge applications, we see that using many chickens can be beneficial if the workload is big enough. And the threshold at which we start preferring multiple processors with respect to a single one is rather low. Here, 1.7 megaops per second, which is basically nothing. Why in this region we prefer to have a single core? Well, because if you have a single core, you have a single core that leaks energy. So at some point, having more stuff will cause some static energy consumption, which will be detrimental to your energy efficiency. Nonetheless, we wanted to have multiple cores. We did all this study about oxen and chickens, but it turns out that it's all about the memory. And again, this is something very much in line to the in and near memory lectures which you're having in the morning, and it's true even in a low power regime. For low workload, having leakage dominated execution means that since the memory dominates the area of the chip, is also the part which leaks the most, while if you have a higher workload, still fetching instruction for all these private memories consumes a lot of energy, even compared to our processing cores. So what we can do, well, we decided that having all these private memories was not the right solution. We wanted also to have a shared multi-banked instruction memory. So now we have a nice simple architecture in which we have multiple banks of instruction memory, crossbars, processing cores, multiple banks of data memory. This is very nice if our application is embarrassingly parallel. Imagine that we're doing compressed sensing. What we do is that we acquire a window of signal, then we do our matrix multiplication, always with the same matrix composed by zeros and ones, and we compute the output. There are no data-dependent branches at all in this application, and each processor is actually executing the same program on different data. So we can just store that into a single copy, and then all processors fetch instructions from the same location. This allowed us to dramatically decrease the requirements in terms of system clocks, because now we have multiple processors, so we can lower the voltage, we dramatically lower the instruction memory accesses, and we also have quite a good impact on the data memory accesses because we fetch from the same random matrices. So All in all these characteristics compound, and we have 88% of the savings in our settings with 65 nanometers technology. But this was a very particular application. It turns out that in this world, not all applications are embarrassingly parallel. The moment in which we have a data-dependent branch, what I just explained doesn't work anymore because we need processors to fetch different instructions. And we cannot know that at compile time because branches can be dependent on the input data. In particular, lockstep execution can be broken by two factors. One are data memory access conflicts, and this is the easy one. If two processors are executing the same program and they want to access two locations in different positions in a bank, this must be serialized. So you need a serializer in between which detects this conflict and just stores first one core, then the other, and then they can proceed in lockstep again. Second condition are data-dependent segments of the code. What we would like to have is that we have a bunch of cores which execute the same instructions, and then a branch happens. Some of the cores will go in one direction, some of the cores go into another direction, but when the control path converges again, then they should resume lockstep execution because this is the most efficient type of execution. So let's see how this flexible single instruction multiple data paradigm can be implemented. Oh, sorry, data memory conflicts. You just stole some of the cores, you serialize the accesses, and then you're good to go. Branches. So we supported that using a combination of instruction set extensions and of specialized data memory locations. Before a conditional branch, cores announce the possibility of the synchronization. Then at the end of a branch, cores announce that they have finished. When all the cores on a branch finishes, then they can resume execution. How does it work? We have synchronization points which are specialized location in memory. And we have a sleep instruction which requires the synchronizer to clock gate a core, and sync and stack, which signal possible desynchronization and resynchronization. At the beginning of a data-dependent branch, all the cores are asynchronous, so they issue a sync instruction. This appends the ID of the core and increases the synchronization counters. Then cores issue a stack, and they go to sleep when they have finished the branch. Every time they issue a stack, the synchronization counter is decreased, and nothing happens to the ID. When the synchronization counter reaches 0, then all the cores are released, and they can continue processing. This is a practical example of an application which uses this paradigm. It is a morphological filtering used to denoise an electrocardiogram signal. And since this application has to detect maximum and minimum in a Windows signal, it's highly data dependent. Nonetheless, our methodology works quite nicely. First of all these sync, stack, and sleep instructions only accounted for 2% of the runtime, so the overhead was kind of acceptable. And secondly, we could stay in sync for most of the time, so we were very efficient in recovering synchronicity among the different cores. So yeah, 45% savings. And this goes to the next stage of complicating things, and here I'm addressing a fully feature-based flow in which we have synchronous conditioning, data fusion, and feature extraction. This part looks exactly what we have covered already, but there is also another part, which are client-provider relationships, in which there is a core which provides data to another core. Turns out that this can be supported very similarly to what we have seen up until now. Again, the producer of data notifies before producing some data, and the consumer just notifies when he's waiting for data, and there is a synchronizer which wakes up consumers when data is ready. How does it work? We need one extra instruction, which is called a SNOP. A SNOP is kind of a special NOP, because what it does, it appends the ID of the core to the synchronization point, but doesn't increase the counter. When our producer core produces some data, decreases the counter and just says, okay, wake up everybody which is here waiting, and then operations can proceed. So for being an operation is quite powerful in this context. Again, example, free lead filtering plus delineation. Here we have three inputs, condition them, combine them, and then we find the fiducial points, beginning, peak, and end of the characteristic weights of each orbit. So there are three cores which we want to maintain in lockstep as much as possible, and two more cores which are in the producer-consumer relationship. Again, less than 3% of overhead due to synchronization instruction. We could lower the system voltage quite a lot, reduce the number of instruction memory accesses and data memory accesses, all this combined resulting quite a lot of energy saving with respect to having a basic synchronization based basically on active waiting. So there is no synchronizer which clock gates and release the processing cores. Another questions before I move ahead? Yes?
So I didn't understand if these synchronization and variable were supported at the hardware level or were just from the software side, and were those in the chip you described before, or just a technique of synchronization for multi-processing?
Can you repeat the question? Sorry, I really didn't listen.
Okay, sorry. Were this technique implemented at the hardware level? So barriers were hardware, counters were implemented in the hardware level, or software?
So they're implemented at, so the question was this implemented in hardware or in software? The answer is they were implemented at the instruction set architecture level, which means that you need hardware support for that, but this is pretty minimal, because basically you need provisions to having a +1 counter and little else. And at the software level, the software developer has to put these pragmas inside the code. We actually provided a library which hides this complexity from the end user, but still we didn't have real compiler support, and we instead used inline assembly for issuing these pragmas. Other questions?
So for the task level parallelism, if we design the chip is a simple this situation, so if we change the task, would the chip also need change?
The question is, if we change the task, will the chip change? No. What we need is just support for these instructions. So we need a special instruction which manipulates locations in memory in the way I explained, and this is some hardware support which needs to be provided, but then an application can be whatever as long as you have no more than 8 cores, because we are just at 8 bits to implement that. You can think about different variants which scale to more cores than that. Further questions? Okay. Now, resiliency. So, edge applications are by and large resilient to errors. First of all, because they interact with the physical world. So the data which we acquire is noisy to start with, is not perfect. So this can hide some inexactness on the type of processing which we do. And secondly, because what we measure is usually qualitative or statistical in nature. So a little deviation doesn't harm the quality of service. So we can use this to trade off between quality of service and energy efficiency. In the techniques which I'm going to explain, I will decline quality of service in terms of correct output divided by total processing. Our scenario in this case was to look at possible errors which are induced by aggressively scaling down the voltage. So when we start to scale the voltage down, the first thing which fails are SRAM memories, and they fail into a statistically predictable pattern. Nonetheless, we had to take into account that once we start to live in a dangerous regime in which we aggressively scale the voltage will not stay constant, but it will start to fluctuate around the non-nominal supply value. So there is a combination of probabilities of failure of different bit cells, and the probability of having a given real voltage while running the application for a nominal voltage value. So this is then the failure probability which we have for a nominal voltage value. Now, once we have bit flips, three things may happen. First of all, nothing happens. There is a portion of bit flips which have no effect whatsoever in the runtime execution. For example, because they flip a bit in an instruction which is unused, or they flip a memory location which is not used by our program, etc. The second thing are silent data corruption, which are non-permanent effects, and here we have a wrong result, but our program keeps behaving correctly. The third thing are unrecoverable errors, and these are system crashes. So masked error, we don't have to do anything, they are masked by themselves. Silent data corruption, we would like to catch those, but is not strictly required. System crashes, all of these must be detected. So we wanted to see what is the minimal amount of hardware support which can allow us to have this behavior. And it turns out that this amount of hardware is pretty small. What we have to do is to keep track of synchronization points. If a processor tries to desynchronize from a branch which has never taken, it means that we had a pretty bad bit flip and we just jumped to a random location in memory. Then we had to check that as we are acquiring the signal, we never overflow the FIFOs, because if that happens, means that one processor is stuck. And then we have some additional checks, like we should never read from read-only parts of the data memory. If that happens, means that some error has occurred, and that we should not access instruction memory regions in which no program is residing. What happens if any of this happens? We just reset the whole thing. We lost some data, we can live with that. As long as we kept going on, we're good. So, what happens now? Well, we can see that there is an optimum depending on the voltage supply and the noise which we have on the voltage supply, which we have the maximum energy per correct output. Here, we are discarding too much, and this is wasting energy. Here, we are investing too much energy in order to compute something, and we could use a lower voltage. And it turns out that when we are at this minimum, the quality of service is still good enough. 90% of what we are computing is correct. And this leads to very nice energy savings in which we are resetting from time to time, we are discarding some data, but if we have a limited battery, after the battery is depleted, we would discard data anyway. So what we want to have is, for a given amount of energy, to process correctly the most data possible. And this is something which is a little bit different with respect to inexact computing due to inexact multipliers or inexact by construction circuitry. Here we are having bit flips which are random phenomena, and we are in a situation in which we have to do the most that we can for a given amount of energy. Next opportunity, sets of intensive computational kernels. As I said, in signal processing, features-based flow, rule of thumb, 90% of the runtime is spent on 10% of the code, so which means that there are some intensive loops, and we would like to accelerate those. How we can accelerate an intensive loop? A good candidate are siege arrays. Does anybody know about siege arrays? 1, 2, 3, 4, 5, few. Okay, you can see siege arrays in two ways, either as an FPGA, in which instead of having lookup tables and flip-flops, you have ALUs during arithmetic operations, so that you can map one arithmetic operation in a cell in the siege array. Or you can see that as a SIMD machine, in which instead of having a linear combination of SIMD units, you have a mesh of SIMD unit, which is two-dimensional, and each unit can communicate with the neighboring one. So it's something which is in between FPGAs and SIMD machines. What we wanted to do was to interface a siege array with a SIMD multi-core processor. This is the structure. So we have our ALUs. Each of the ALUs have a small register file, and they can take operands from the neighbors or from memory, and each of these ALUs can do some arithmetic operations. Since the number of control is limited, we can afford to have multiple control words for each unit, so we can have a set of configuration registers. In this case, each one was 32 bits, and this register can be cycled at runtime. So there will be a program counter which dictates what each of these would do, and depending on this program counter, each of these ALUs will do something useful. Now, having a multiple connected to a siege array means that multiple cores may require acceleration. And in order to take advantage of them, we actually provided multiple program counters, one for each column. When a processor requests an acceleration, also declares how many columns it would like to map its acceleration routine, so that we can partition the siege array fabric among multiple acceleration requests. The way processors can issue an acceleration request is by using, again, an instruction set extension, which is just accelerate ID of what I want to accelerate, in which, by doing that, the configuration of what we want to do will be loaded into a column or into a set of columns, depending on the complexity of the loop that we want to map. This works pretty well for a set of applications. So here are the application themselves, and here are the different loops which we accelerated on the CGRA. And you can see that in all cases, we could have pretty healthy energy gains with respect to executing the same loop in software. Then we got even more ambitious, and we said, okay, we can have execution in lockstep among multiple processors. Why cannot we have execution in lockstep even onto the CGRA, so that we are mapping the same acceleration on different data using some specialized hardware? Actually, it turns out that you can do that by providing multiple ALUs inside of each processing element, and these multiple ALUs share the same configuration words. It works again pretty well. There are diminishing retards as we augment the number of ALUs which are present into each processing unit, but nonetheless, all this doesn't require a lot of resources. If we have 3 ALUs into each processing unit of the CGRA, into each cell of the CGRA, we just had a 44% increase in the area requirement. Now, we have the CGRA, we have the multi-core processor, we have a strategy to do in exact computing, and now we can just mix and match. For example, we may have a multi-core with a CGRA plus in exact computing, and here we will have that gains compound, or we may have the CGRA which is specialized with some custom instructions, and so on and so forth. So the nice thing about architecture research is that once you have developed blocks, it becomes easier and easier to develop further blocks and to see how they interact with each other and how different opportunities can synergize in order to have even better results. An implementation of the architecture which I just shown you is available as open hardware. So if you want to take a look at it and start playing with it, it's available on GitHub. We are now working into a slightly different implementation, and what we are trying to do with this architecture, we still have processing units. In this case are called RCs instead of PUs, but they are basically ALUs. But we try to interface them towards memory while minimizing wire lengths. Why this is the case? Because we're looking at advanced technologies, and for advanced technologies, wiring is a big problem. So we would like to have regular architectures in which the length of interconnects is minimized, and these are very regular. So this is something that our PhD student, Lara Orlandig, is very proud of, and rightly so, because she was able to actually place and route the register file of the CGRA in the HiPEAC A14 technology node, which is a very advanced technology node, and the actual placed and routed succeeded with very short wire lengths. Using a completely automated tools from Cadence, this just failed, so she came up with guided techniques in order to achieve this placing and routing. Now, I said that we executed loops on the CGRA, and I glossed over on how this is actually done. So compiling for CGRAs is challenging because you have a 3-dimensional target. We have a 2-dimensional mesh with nearest neighbor connection, and then you can cycle configuration at each clock cycle. So what I'm doing here, I'm taking a 2x2 mesh, just for simplicity, and I'm displaying that into a line. And here is the timing dimension. If I want to map a loop which has 4 operations, and these are the data dependencies, what these operations are doesn't really matter. I can map them like this, and then I can partially overlap different iterations of my loop. We have the red iteration, the blue iteration, and the green iteration. If I keep doing that, I arrive at a point which is called the steady state, in which this scheduling repeats itself over and over again. In this example, the steady state is only 1 clock cycle, but it can actually be multiple clock cycles depending on the amount of resources which we have and the data dependencies which cross the iteration boundary in the data flow graph. So, and in this steady state, I'm executing on 2 different processing elements, different iterations of my loop. In this case, this node is from the green iteration, blue iteration, and red iteration. There are a number of automated tools that do that. In our framework, we integrated a tool which is called setMapIt, which is being developed by the University of Lugano, and in particular by Christian Tirelli, which is hosted here by the summer school. So if you want to know more about compiling for CGRA, you should actually ask him. How does it work? It takes C code and then uses LLVM to translate that into an intermediate representation. These 2 representations are equivalent, just this is human readable, this not much. Then this representation can be translated into a graph in which we have operations and dependencies among operations, and the black arrows are from the same iteration, the red arrows are from one iteration to the next one. And this is why these arrows can go upward, because they are across iterations. From this graph, we can actually achieve a schedule, and we start from saying, okay, for each operation, how soon it can be scheduled and how late it can be scheduled. And we know that each feasible solution will be in between this as soon as possible and as late as possible scheduling, and the superset of all possible solutions are what is called the mobility scheduling. All this information can be fed to a SAT solver, which takes constraints and the graph as input, and then produces a feasible solution if one exists. What are these constraints? Each node in the DFG can be mapped only once. 2 nodes cannot be on the same processing element at the same time, and each node predecessor or successor must be assigned to a neighbor or on the same PE. So we have to take into account the connectivity in between the different processing elements. 2 processing elements which are far away don't have a direct connection among each other, so we have to take that into account when mapping operations. This is the same thing in math. If you want to know the details about this formula, ask Christian, please. Okay, so the last thing that we have to do is to look at register allocation. Registers are present in each processing element to store intermediate variables, temporary variables, and there is a limited number of registers in each processing element. So we have to make sure that we are assigning a register to each variable and that our mapping is feasible. So these are results on some target application compared with state-of-the-art solutions, and we can see that setMapIt works pretty well, so it can map more application and with better performance. The performance here is expressed in terms of initiation interval. What is the initiation interval? Is the distance in terms of instructions between the start of a loop iteration and the start of the next loop iteration. So basically, how much we can compact the loop nest so that we can issue new loop iterations as fast as possible. And here it is expressed in terms of distance, in terms of instructions. Be aware that this is indicative of performance, but abstracts away everything which can possibly be related to hardware implementation. So if you want to know the full story, then you have to map your loops into real hardware. And this is what we did. And we would like to have a nice linear relationship between what are the compiler level metrics, initiation interval and utilization, and the hardware level metrics, number of clock cycles and energy consumption. It is not really like this because the devil is in the details, but still we have that solutions which are dominated with compiler metrics are still dominated with runtime metrics, hardware runtime metrics. So by just looking at what the compiler tells us, we can already discard solutions which are suboptimal, which is already something. It also points out that there is a gap to bridge here, and we are actively working on that. If we see each other in some time, hopefully we will have a solution for bridging this gap. Questions? Okay, so now I'm turning pages, and instead of looking at solutions for features-based flow, I will start looking at solutions for machine learning-based flows. And the first thing that I want to look at is that machine learning is resilient to a large degree towards errors. How this can be leveraged? Well, I think that is known to many of you that machine learning models can be quantized pretty efficiently and can be pruned pretty efficiently. So entire weights and filters can be removed from a model, and if we do that in a smart way, we have minimal impact on the quality of service, or we can represent data with just few bits without almost no impact on accuracy. Before starting to optimize, we would like to maximize this robustness. My PhD student Flavio Pozzina looked at way to do that, and he looked at ensembling. What is ensembling? Is replicating models in their structure and training them starting from different seeds. If you start training them from different initial conditions, you will have different weights at the end of the training, and this increases robustness. On the other hand, we are increasing the size of the models n times, which is not exactly what we want to do if we want to optimize the execution. So is saying, okay, I want to have ensembling, but with zero overhead. I take my model structure, I just prune by removing a portion of the filters, and then I replicate an instance and I train them. If the pruning level and the replication level are the same, I don't increase the workload requirements, but still it turns out that I can increase performance. These are examples from multiple benchmarks, starting from a positively ancient LANet 5 up until MobileNet, which is something which you may find nowadays into edge devices. And we can see that ensembling really can improve performance with little sacrifice in terms of accuracy. Oh, sorry. There is one thing which I forgot to mention. So we wanted to increase robustness. So here we were inducing bit flips into the weights and see what happens. If we have a monolithic model, the accuracy just drops like a rock. Instead, if we have assembling, we are more robust towards those bit flips. So we could live in a dangerous region in terms of voltage while still maintaining quality of service. Yes?
Could you explain why for higher voltages the 8 ensembles perform worse than the US ensemble?
Yes. This is because, so the question is why this green line doesn't reach a good level for high voltages. And the reason is that here we are pruning our model very aggressively. We are using a model which is 1/8 of the initial one. So it's a very small model as an instance. So even if we replicate it 8 times, our quality of service and so our accuracy would suffer. Other questions?
So the pruning to different small portions is randomly. So for the pruning to different small portion of the network is randomly.
Yes, pruning is, so how we do the pruning? Pruning is done before training. So it's done on the model structure, and we drop randomly a portion of filters from the model structure.
For example, if you have 8 small network, do this 8 small network understand or?
So these small networks will behave appropriately up to a certain point. What we are seeing here is a network which is starting to become too small for the application at hand. So the green line reflects the fact that our single instances are just too small. So maybe having 8 small instances is just too much. You're better off with 4. But it also depends on what is your voltage regime. If you have a lot of bit flips and you can live with an accuracy degradation of just a little bit, then by all means just go with small networks replicated many times. Other questions? So this points to a generic optimization loop in which we may have an input convolutional neural network, and this is pruned and replicated in order to have a multi-instance network. And this then goes into an optimization loop in which one instance is taken one at a time, and then from this instance we measure which layer is more robust towards optimization using some kind of sensitivity analysis. Then for that layer we can further optimize, and optimizing can be doing some quantization, some pruning, some codebooks. We will see many different ways of doing that. Once we do our optimization, we have perturbed our instance, so we can do some fine-tuning to try to recover accuracy from this perturbation, and then we measure if our accuracy is good enough. It is good enough, we accept the optimization. It is not good enough, we just roll back and we just pick another instance or another layer of the same instance. When there are no more optimization moves possible, we are done and we have our optimized ensembles. This is kind of an abstract optimization loop. We will see how this can be realized in practice with different strategies. So please remember this one. We will see that in architecture-dependent ways, for general purpose system, and when we will look at compute memories, and also something a little bit different, which is called software-defined SIMD. So let me just go through codebooks first, because we said, okay, we have this optimization, and we may use accelerators to support different optimization strategies. But it turns out that the best accelerator maybe is no accelerator at all. And our challenge is to support quantization with very few bits while having a machinery which doesn't support arithmetic with few bits, which is actually usually the case for general purpose processors. Usually, you don't have 3 bits arithmetics or 4 bits or 5 bits arithmetics in a general purpose processor. So even if you quantize your model, but you don't have an hardware which supports that quantization level, you're just wasting accuracy for no reason at all. What is the trick here? So here we're saying, okay, actually, I don't want to represent my model in terms of weight values, but I want to represent my model in terms of indexes, and these indexes index a table containing floating point values, but only few of them. So each layer may contain 4 floating point values if it's using 2-bit indexes, or 2 floating point values for 1-bit indexes, 8 floating point values for 3-bit indexes, and for each layer I will have a small table containing those values, and all the many weights are represented as indexes in that table. How to do that? We can use some clustering in order to understand what are the actual values which we would like to have onto those tables. If you think about it, if you have quantization, you can represent fixed numbers at homogeneous intervals. While if you have a codebook, you can have a fixed amount of numbers, but they can be anywhere among the values which are representable in the floating point format. So this is our optimization loop again. Now I take an instance, I do my sensitivity analysis to understand which layer I want to process. I pick one layer, I do some clustering among the weights which are available in that layer, and then I fine-tune by doing some training epochs again. I do clustering again, because by fine-tuning, the values of the weights will diverge. So I have to fix them again by to the numbers which are available in the table. So here I do clustering, for example, to 8 different values. By fine-tuning, all the weights will go all over the place. I have to do clustering again to put them into 8 values, and then I measure my accuracy. It is good, it is not. I either accept the optimization or I roll back. Yes?
When you do the method, you do it with the floating point values before like get or whatever.
So all the values in the will still be floating point. The catch is that there will be a small number of different floating point values. So during training, you can keep everything in floating point. When you do the clustering, you will just pick the centroid of some number of floating point values. Fine-tuning, they will diverge, but you do clustering again. Other questions? I know that I'm getting out of time. Let me finish this topic, and then I will stop here for today. Now, in order to investigate that, we look at different benchmarks, and we measured the baseline accuracy. We wanted to implement those both in general purpose architecture and to in edge architectures, so we re-implemented the inference stage in C++, so that then we could compile and run them onto microcontrollers. So this is an example for the VGG16 case, and we can see that for a given bit width, we can have way better results by using codebooks with respect to using quantization. Just be aware that the meaning of bit width is different for quantization and for codebooks. In the case of quantization, these are the bits which encode a value. In the case of codebooks, these are the bits of the index into the table containing floating point values. Nonetheless, the overhead for storing the tables is very small because those tables are small. If you have 3 bits for the indexes, means that your table is 8 elements for a whole layer. And for a bunch of different benchmarks, we have basically the same result. Codebooks just work. Now, one semi-surprising effect is that by using codebooks, we also add noticeable speedups, even if we introduced one level of indirection, because instead of having value readily available, we had indexes which we use to index a table. Why is that? Well, that's a question, but the answer is actually here, so I wouldn't even ask you. The thing is that if we're using 4 bits for our indexes, we can fetch 4 indexes as part of a single word. And this increases quite dramatically data locality and decreases the number of cache misses for a given cache size. Actually, the amount of speedup which we had was more and more noticeable the more complex the processor was in which we run the thing. This is kind of not the intended purpose because we wanted to do something for edge low power domain. Nonetheless, it's an interesting effect. Not always adding algorithmic complexity results into a slowdown. So I'm very much late and out of time, so I would stop here. Tomorrow, we will see something which is called bit-line computing, and it is a way to have in-memory computing for machine learning models which are heterogeneously quantized in fine-grained so that we can process in parallel by using operands which can be of any bit width. Do you have any further questions? Yes, please.
Small question about the percentage of the energy consumption memory according to CPU.
Can you please?
Do you have any idea about the memory energy consumption in your use case? According to CPU.
So, at the CPU level, you need to do few more instructions in order to extract the index from a memory word. So if your index is 3 bits, you would have, for example, a 32-bit memory word, and you have to do some masking and shifting in order to extract 3 bits fields. But you have way less memory accesses. And this more than compensates the extra instructions that you have to do. Because those extra instructions are all local, so they don't impact the memory. They can be done just with the local register file. Other questions? Okay, so in any case, I'm available around in case you have more. Thank you very much. Sorry for using few more minutes of your time, and see you tomorrow.